Space is a vast, cold place where it's hard to get to, and it's not a particularly friendly place for humans and the stuff that we build. However, Joe Barnard, our guest here today, is trying to get there anyways. And as far as he can, that is, because he's using model rockets to do this. Joe runs a program called BPS.space where he showcases his journey learning how to build model rockets that approximate the real thing. And as you'll see, he's basically trying to do the same thing that the SpaceXs of the world and the Blue Origin and the NASA shuttles in the old days. Basically, he's trying to control model rockets in the same way that these modern rockets also work, with the goal of maybe working there someday or maybe just continuing to make great videos about it. The thing about watching someone in the field of rocketry is that the failures are very apparent and spectacular because everything blows up. And that's a really fun thing to watch. Obviously, you don't want to see someone fail, but it's really rewarding to watch Joe break down what went wrong when his launches don't go well. And I think he's a great example of someone who's using electronics to not only achieve this goal, work towards this goal, because it really is this progress thing that he's doing, but also that he's measuring along the way. And so he can actually see what went wrong, look at measurements, reverse engineer what happened, and then try and fix it for the next round and iterate. So all of these things are these great lessons in, practical engineering to try and make model rockets look like real rockets. Joe is completely self-taught, and it's really impressive to see how he goes through and researches these things and builds these things, builds his own electronics. He actually sells the electronics so that other people who want to do rocket control can use some of the electronics that he builds. And so he shows in this upcoming episode his progress and how he started from soldered together breadboards all the way to the custom electronics that he's using. And they're pretty advanced devices that he's building now. So I hope you enjoy this great walk through explosive failure and custom electronics and a learning process that Joe shows on camera in a beautiful way because he's a great filmmaker as well. So enjoy Joe Barnard in this episode of the Contextual Electronics Podcast. 5, 4, 3. Sorry. I just figured that people would like, I don't know. Hey, Joe, how are you?
That's great.
How are you doing?
Hey, Chris. I'm good. How are you?
I'm here today with Joe Barnard, and if you don't know his channel and his mission in life, it seems like, Joe does rockets. He talks rockets all day long, like he mentioned to me earlier. And Joe, I'm really glad to talk to you here because I think it's an awesome application of electronics to a very, very specific thing, but has a huge impact on it, it seems like.
Yeah, it is incredibly niche, but I have a ton of fun doing it. And yeah, you're right. I talk rockets all day long, so this is great. Thanks for having me on.
I'm glad to have you here. So maybe just a quick recap for people that don't know BPS.space and your mission.
Yeah, absolutely. So I'll give you the super quick, try to fit it in 2-minute rundown. I studied music in college. I've always kind of loved music and engineering, did first robotics and stuff like that. And I studied music up in Boston. And about halfway through college, got into videography a little bit, which is how I acquired a tremendous number of fancy cameras. And then in 2014 and 15, SpaceX was starting to get serious about trying to land things. That's Elon Musk's rocket company. And it was just on Facebook or something. I was scrolling through, I saw a video of it, and it just hooked me in. So I started going way down the rabbit hole, as you do when you find a new thing that you're interested in. And I decided I really wanted to work for them, but I knew I had a music degree that wasn't going to fly super well when you're like, hey, can I apply for this, really exclusive aerospace engineering job? So I figured instead of getting another expensive degree, I'd start this project to try and launch and land a model rocket like a Falcon 9. And I thought it would take me 3 months. It's been 5 years. Still haven't done it. Getting real close.
Yeah.
But I've started sharing that journey of what I'm learning and what I'm working on and what I'm trying to do, what works, what doesn't, all on the YouTube channel BPS.space, which has become one of the most successful parts of this whole project is just the channel itself documenting what I'm doing. And that pretty much brings up to speed in a super succinct way.
Yeah. Oh, that's great. And I think people who have watched the podcast so far or listened to it so far, they'll hear, a very thematic element here, mostly of you sharing your work. And that part is fantastic because, it shows your learning process first off. And then also it shows, as you progress, kind of we get to watch alongside you and learn the things that you're learning. Maybe not as viscerally, but like, we get to at least hear some of your lessons learned. So are there any like pop out at the beginning of like, oh man, if I only would have known on day one, blank.
Okay, so I mentioned this on a call I had with someone the other day, but I think let's just give it a try at the risk of
Sure.
sounding a little ridiculous.
Yep.
The hardest part for me of all of this was that I just didn't have an engineering background. So like I liken it to what if you have no idea what a stop sign is?
Mm.
Like what in the world a stop sign is, and you're driving down the road and you see one and you want to know more about it. What do you search? Do you
Right.
search like red shape road, red octagon Google Images? Like and you have to do all of these like bizarre misses of searches on Google to try and find out what you want to do. And people don't publish a lot of things about rocket guidance for generally good reasons. And
Hmm.
so the hardest part, like the biggest lesson, is just how to get real specific and how to pick out the little golden nuggets from Google searches.
Mm.
That's a pretty specific thing, but
No,
I guess that would be
literally we talk about
one of
that on the
the.
course all the time. Knowing what to Google for,
Okay, cool.
yeah,
Yeah,
is in the electronic space, right? Of like, I need a thing that like I know I want to keep it at a certain voltage, but I don't know how to do it there. And it's like it could be a regulator, it could be a clamp, it could be all these different things. But yeah, you just don't have the terminology, and we
yeah,
always default to like Google image search specifically,
yeah,
like
man.
images. I don't know why that seems to be helpful. Maybe it's just because of the human brain of visual nature, but
Yeah, and like 9 times out of 10, you're going to end up on Stack Exchange
yeah,
on some like obscure answer.
right, right.
Um, yeah,
I wonder about how people were doing this before. I guess there wasn't this, like before Google, before like search engines in general. Like, you go to a library, you hope for the best. You not, you find that graybeard that used to work at NASA or something. But like, yeah.
yeah. I mean, it's not just Google. Like I've learned things from mentors. I've learned
Hmm.
stuff a decent amount from textbooks.
Hmm.
But Google searching has been like the most valuable thing. And also, it sounds crazy, but like there's there's a YouTube tutorial for anything.
Sure.
There's a ton of people who put up videos on control systems and electronics. How I learned to code, at least at first, was all from a video series.
Mm,
Um, yeah, you can learn anything.
that's great. That's really great. So do you still have this? So 5 years in, a growing successful YouTube channel, still want to work at SpaceX or no?
I wouldn't say no to it. I mean, that sounds. There's no way to talk about this with like a low ego.
Well,
So
Elon,
yeah,
call me. We'll talk. You know.
we'll talk. No, no, no. So I would love. I want to work in the real aerospace industry.
Mm,
SpaceX is not the only company that I would want to work for now, though.
sure.
And the thing that, like, I don't think the YouTube thing is going to last forever. I'm having a ton of fun doing it, and I wouldn't give it up until it's clear that, like, all right, this isn't going to work anymore.
Mhm.
And that day will probably come. But when it does, I think I'd want to work at like a pretty tiny company
Mm,
where you have a lot of control.
yep.
Like my favorite part of this stuff is that I'm not specialized in anything. I know how to sort of fake my way through electronics. I know how to fake my way through PCB design and a bunch of these things. And so working at a company where I get to have my feet in a couple of different things, that would be the goal. Um, and yeah, there's a couple of things in mind. SpaceX
Cool.
might be one of them, but
Cool. Oh, that's
yeah,
great. I mean, I think that's another interesting thing too of like you start with these like high level goals like this. And, I think about like my starting days in electronics and I was like, oh, I want to like design a cell phone. And then like, you know, then I learned that like to design a whole cell phone is of course, kind of ridiculous, but there was pieces of that kind of like played together and like, but that was just that starting, thing that I was shooting at. And then eventually along the way,
yeah,
I figured out other paths that were interesting and what might have been a good fit. So yeah, that totally makes sense.
yeah, yeah.
Okay. So I have launched exactly one model rocket in my life, and it went very poorly. And it was about, I think, 20 plus years ago. I'm guessing things have changed, and specifically, you are changing some of these things. Could you kind of give us a quick rundown of what the state of model rocket industry is, and then what you're trying to do with it?
Yeah, this has gone through a couple of iterations, but I'll try to run it down. So most model rockets, they use these fins. I wish I had a good example, but most model rockets, actually the Saturn V, right behind me
Mm.
here, uses some amount of aerodynamic stability. But basically, you have fins at the bottom, and it's essentially a dart, right? You have fins at the back. You keep the center of pressure behind the center of mass, where the vehicle will balance, and it naturally will stabilize in the air. And this is great because it means you can build them really, really cheaply, and they will usually fly straight. Usually being the keyword. But uh, in order to do this propulsive landing thing, you have to change a few things. Like when you get close to the ground, you're not going very fast, and you lose that aerodynamic stability. So what you have to do is what most real space launch vehicles will do, which is called thrust vector control. And it's not necessarily a new thing in the hobby. There's someone who figured it out in the 80s with like 80s electronics, which is incredibly impressive.
Mm-hmm.
But yeah, it's not necessarily a new thing. I just have I'm the only I'm the only fool who has spent this much time and money on it.
It seems like
But
yeah, no, you have a very specific focus on it, and that allows advances, right? I mean, like to have this focus on it.
yeah, yeah. So it, it's going to be hard to do without the thrust vector control. So the state of model rocketry now is still almost exclusively the rockets with fins, but there's a tiny little group of people who are trying to do this TVC stuff. And just to address a few things, it's not practical. It's not that useful for most model rockets. You're unstable after the motor burns out. There's a whole host of things. Like it's expensive, it's heavy. The goal isn't really to replace model rocketry with this style, and I don't think it's practical to do that. But there's a tiny little niche sector of it that's sort of growing, and that's kind of the lay of the land, I think.
Okay, yeah, that's great. That's great. And I mean, it seems
Yeah.
like you are also working on things that are kind of adjacent, but still have this technology in it. So I'm going to just share some current stuff on screen here. This is
Oh yeah,
the
yeah.
hovering. What is it called? Sprite.
Sprite.
Yeah,
Yeah,
yeah.
yeah.
So
So this is around this time last year, a little earlier. I took a look at my flight control software, and just I reached a level of horrified with this whole structure of it that I was like, I gotta stop launching rockets for a bit, and I gotta revamp my control software.
mm,
And this is my efforts to write new flight control stuff. So now you can see this is all live telemetry. Like this isn't plotted after the fact. It's being piped in live while the vehicle is flying. So we've got live telemetry.
yeah.
The controller on it, for anyone who does controls, it's now MIMO, so it's multi-input, multi-output.
Mm,
We're trying to control position, horizontal velocity, um, and so Sprite was a like development test bed for that. So it's a rocket adjacent thing. I don't know what I guess you could classify it as a UAV, and you
yeah.
have to register it.
Kind
But
of reminds me of like the Moonlander game that used to have to like on like old Windows machines, like the Moonlander.
yeah,
You know, just instead of using arrow keys, it's self propelled
yeah,
and everything else, right?
yeah. And like this thing it never went higher than I think the maximum that I ever flew. It was like 10 meters, and then it started running out of battery, and I got lucky and caught it out of the air. But yeah, like the whole goal was just to refine my control stuff. And then if you have any of the most recent flights of what's called Sprint, which is very confusing because the
Mhm.
previous project is Sprite, the Sprint rocket used all of those things that I had learned on the Sprite like UAV test bed, and I put it back into a rocket. So my rockets now use GPS to like steer down a corridor and make sure they stay straight up. Um, this is one of the launches where I did a pitch over, so it turns over to the left here intentionally,
hmm
um,
Right, because that's part of
and
like the escape velocity type of thing, right? Where you see like the
yeah,
space shuttle would be like on its back then as it's going out of the or is that I'm not very good with terminology, so tell me if I'm saying
no,
anything
no,
wrong
no,
here.
yeah, you got it. That would be like the gravity turn, and at
Okay.
this scale, we're not we're not going to orbit. We're
Right.
not
Still
even
a lot of
getting close.
gravity.
But I mostly just did it because it was kind of fun to
Yeah,
try.
yeah,
You can
yeah.
actually see the motor in the bottom left there moving around to
Oh yeah.
steer it on course.
Mm-hmm. Mm-hmm.
Um, yeah, and so that's kind of where I'm at. And then the next step is trying to bring back the propulsive landing stuff. I took about a year break
Mm-hmm.
on it to, again, like focus on let's rewrite the code base, let's make everything a little bit cleaner. And now I feel like I'm ready to give it another shot.
Mm.
Uh, yeah,
Can you tell us a little bit about the so again there's a ton of terminology here. Like you said, it's this niche type of thing that puts together electronics and control systems and propulsion and chemical whatever. But like in the field of avionics and the propulsive stuff, like you'd mentioned like control like sorry I guess maybe what is the hard part about control systems in this context, right? We were looking at that software and there's all this mapping, but it seems like there's also feedback to that as well, and it's acting based on that.
yeah. I mean, the hard part is, I think, I don't know if I can pick one. It's all of it. So the electronics are fairly straightforward. It's not too complicated to put together a printed circuit board with all of the sensors that you want to use. The software isn't that bad if you know exactly what you want to do and you have familiarity in the language. The control system is hard because you like with a rocket. Okay, so with the development testbed, the reason it's a fan and that I'm not using a rocket motor is that I want to be able to fly it again and again and again and again in the same day. With a rocket, you're burning, rocket motors that cost $30 each time,
Mm,
which is not something that makes a whole lot of sense. So the hard part about controls with rockets is that you have one shot. So what you have to do is develop a simulation of how physics how physics be on the rocket before it actually flies. And that's where a lot of my time is spent, especially with the landing stuff of like, okay, cool, we have this amount of thrust at this time with this variance. So we randomize like, okay, what does our burn profile look like? And then how do you take the orientation of the vehicle and generate a command to bring it back to upright, but without doing it and overshooting?
hmm.
And if you look through my channel, you'll see, you don't have to do it now, but if you look through my channel, you'll see all of the difficulties in trying to do this.
Right.
It's very difficult. I mean, just to actually, you can bring this up. The most recent sprint flight, the 1 kilometer shot, it's flight 10. Like everything worked pretty well until I didn't do a good job in the simulation, and so I didn't accurately enough. ac- I didn't accurately simulate the aerodynamic forces on the vehicle, and you can go ahead and play it. When the vehicle launches, it looks pretty good. We have decent stability. Um, we're under control. We're coming back to a center point, and
Hmm.
then as the aerodynamic forces increase, we get this oscillation that I just didn't see in the simulation beforehand because I didn't do a good enough job modeling
Right.
how these forces would act on the vehicle.
Yeah, that's a great
And I did
example
get it
too,
back. It's fine,
because of
but
the overcorrection type of thing. So like when I think about like control systems, uh I think about like op amps and things like that where things start to oscillate, whatever. But it really is all kind of the same thing, where it's basically the example I usually give is like you're in a shower and for some reason there's a really big distance between the knob and the shower head and it's too
mhm.
hot and you turn it really cold and it's too cold and then you turn it really hot and it's like the time between when you sense the temperature and then you adjust it and how fast you adjust
Yeah,
it.
you have like an actuator delay.
Yeah, but all
Yeah,
that stuff you're saying has to be modeled in there so that you could try and accurately have a good shower.
yeah, that's a great example. But yeah, no, that's exactly right. If you don't, like there's not unfortunately there's no magic button that says hey, make this thing work, but you increase the fidelity of your simulation as much as you can so that when it's time to fly,
Hmm.
hopefully things just pretty much look like the simulation, but
Right.
it's very difficult to get to that point.
Right. Well, and we could just as easily queue up the SpaceX videos of things that blew up and things that, like there are, yeah, this is not a, not, not isolated to BPS.space. It's also just rocketry in general. It's just a lot of learning because you don't know about that rattle that might happen that throws everything off kilter. until it happens, and then you got to work that back in. It seems
Yeah,
like.
and it's not even just the simulation too. Like on that flight that you just showed, you can play it again if you want.
Hmm.
But I didn't conformal coat the
Oh
boards.
yeah, this
So
is
the
interesting to me.
PCB
Yeah,
that
yeah.
yeah, the PCB that flew it. This is one of the development versions, and it's actually got quite the burn mark on the bottom there. But
Nice.
we don't have to talk about that. Anyway, I didn't coat the board that flew on flight 10 here, and so right around right near burnout, we actually the navigation computer just dropped offline.
Mm, yeah.
And the leading theory based on like ground testing and things like that is that the I2C bus that connects the navigation computer and the main computer got jammed, um, and you can see all of the lines go flat on telemetry except for a few points of data, and that's the navigation computer just dying in
Wow.
the air. And it's all these things that like that's not represented in the simulation.
Mm-hmm. Right.
Or
Right.
what if your servo is a little bit slow? What if you didn't connect your wires correctly?
Right. Right. Yeah. And so can you kind of explain those terms as well? So you mentioned conformal coding, and you mentioned I don't forget the second thing what it was. But what is conformal coding for people that don't know?
Conformal coding, I'm fairly new to doing it, but basically you take some, there's a couple different chemicals you can use, but I use silicon. That's a pretty popular one.
Mm-hmm.
You take it as a sort of a liquid and you just brush it over your board, and it's not conductive at all. But what you do basically is you're coating your board in this silicone, and by doing that, you help protect it against the environment. So if you have really sensitive tiny electronics on there that have very tiny pitched pins that are very close together, what if a stray piece of metal falls on it and shorts it out? That's not going to be good for your board. So by coating it, you rule out a lot of possible failure modes. And it does make it a little bit harder to work on, but generally speaking, it's easy to reverse.
Mm-hmm.
So,
Mm-hmm. Yeah.
and then the other thing I mentioned was the I2C bus that I think,
Mm-hmm.
and that's just a method of communication between two processors.
Sure. Yep. Yeah, that's great. I mean, yeah, those kind of things where you don't know about them till they're there, and then yeah, they. But you have changed that on the most recent version. I think you talked about this in the new board that you've been creating as well.
Yeah.
The Ava, that's right.
Yep. So AVA stands for All Vehicle Avionics, and the goal is in the name. I want to build. I built this board to be able to fly whatever I build. So in the past, if you want to, at some point, you can bring up the page with all of the different PCBs that I've built. But this is the most recent one, and so it's got pretty much every sensor that I need, all of the outputs that I need. It's set up to try to be future proof. Um, yeah,
Yeah.
I can't remember what the question was.
Oh,
Sorry.
I just had mentioned that you talk about it in this video as well about how you have to conformal code. I think I was thinking about that you have a UV light where you show you're
Yeah.
curing the goop on top of the board and really telling where it is, and that's really good use of all this stuff. So yeah, but yeah,
Yeah,
I
and
think yeah, go ahead.
I brought it into the. I'm actually pretty proud of this. I did just a ton of aggressive testing on trying to make sure that humidity is what killed that flight that we showed earlier.
Mm-hmm.
And so what I did is I brought it into the bathroom, and I turned on the shower for like 20 minutes with a little humidity sensor, and I was able to get the uncoated board to fail in the same way at high humidity, and the coated board was fine.
Yeah,
Um,
that's
so
awesome. That's really great.
yeah,
Yeah, I mean, and that's what testing's good for, right? I mean, so
yeah,
yeah, and so you'd mentioned this other uh, page you have of all the development, and this kind of shows. Oh, this one, sorry, the avionics page. So you actually
yeah.
show kind of the progression from the start. So what were we starting with here?
Well, this is the first. This is actually not the first computer I flew. The first thing I flew was just pins, like what are they called? Like little jumper pins plugged
Mm-hmm.
into a breadboard.
Oh wow, yeah.
Um, and that's not a good idea because in high vibration environments, like that's not going to be good.
Right.
Um,
I usually
so
don't even
then
trust it on my
this.
bench, let alone on a rocket. So
Let's see if I can find it here. I've got all of the computers I've built previously. You can see it's in a DigiKey box,
yeah,
but they're
yeah.
just all.
That's where they
There's a
belong. You know, it's like
That's the
it's like a home
graveyard.
base. You know.
Yeah, I don't know if I can find it. Well, I can find a lot of the early ones looked like this though,
Yeah.
and you can probably see it on the page too.
Hmm.
But we've got like a little teensy microcontroller, a little Bosch IMU, just some relays on there.
Yeah. I saw some Adafruit
Um,
breakouts, stuff like that.
yep, yep. And then some of them look a little worse. This one's on the page too, but I'll bring it out just to show you. This is maybe the worst thing I've ever done.
No, it's the
Um,
best thing. Come on, you show your work. This is amazing. Like it's awesome. Yeah, it's
from very humble beginnings. This is
yeah.
cursed.
But
But
okay.
anyway, yeah. So the page, if you want to scroll down, it shows the sort of improvement over time. Things get a little less sketchy as you scroll down,
Hmm.
and as I get a little better at building things.
Yeah, I
I
like
think
this
after
too
this,
because it's a showcasing of like not the need for this obviously worked, but like in terms of reliability, repeatability, all those things, starting to make your own circuit boards like you show here, it really does help for
Mhm.
that sort of thing. And I'm guessing you had started learning a lot in this case in this way.
Yeah, and actually, right around there, when I started doing the PCB, the impetus for that was I was just dumping money into this project, and it wasn't working very well.
Mm.
Like I could get good flights, but I couldn't see a path forward with it. So I tried to develop a product
Mm.
called Signal, which is you can see like the early beginnings of it here. And
Hmm.
the goal was to build a kit so that if you wanted to add thrust vector control to your rockets and you didn't want to spend like a year developing it for yourself, you
Right.
could just
Just
purchase the
buy
kit
it
and
from you.
fly it.
Yeah. Right.
Yeah,
How
yeah.
how
And
how big
so
would you say the industry is? I mean, like how many rocket enthusiasts are there?
well, I estimate there are about 10 to 15,000 like active members, active people flying in the U.S.
Hmm.
But I don't have a whole like I did a bunch of market research 3 years ago when I started selling these kits,
Hmm.
and that's the number I settled on. But I mean it's growing.
Yeah.
Um,
Totally. Yeah.
it's growing by like NAR memberships, and NAR is the National Association of Rocketry. That's the sort of front runner of organizations. It's growing by that metric, and then it's certainly growing in this like little odd niche thrust vector control group of
Hmm.
people.
Hmm. Like the ones who specifically want to control very, very specific elements of it, that kind of thing.
Exactly, and that's a fraction of a fraction
Yeah.
of the whole, people, everyone doing model rocketry,
Right.
but
Right.
it's there.
Yeah, that's great. And I mean, that's even a much smaller group than YouTube subscribers that are interested in just watching. And like, you never know when someone might like tip over and be like, "Hey, look, I think I can do this." Right? Watching Joe do
Hmm.
this, I think I can do it as well. And that's the best way to get people into the hobby. I think like to bring more people
Yeah,
in. So
yeah.
it seems like it continues. So for people just listening, we are scrolling down this page, which we'll have linked in, of course. It's BPS.space/avionics, but it's still going here. So what were you thinking as you were trying to add stuff on here? Like what were the requirements that you had to put on a board like this? Is it just the controller or sensors as well, or what are you trying to do with it?
It changes. So the signal boards are all built to be a product. So what I'm specking around primarily is this component widely available?
Hmm.
Is it necessary? Do I actually need it on there? That's what a lot of the signal boards are doing. And if you want to actually just scroll all the way to the bottom, you'll see the final iteration of it, which is Signal R2. That's right here.
Hmm.
And so I mean, this design was locked in I think 2018,
Yep, looks like
um,
it.
and I'm about to ship out another order of them. They're still working just great, but if I were going to do it again, there's a bunch of things I'd do differently. But
Hmm,
yeah, I mean, for most of the signal stuff, what I'm specking around is more of a manufacturing thing. Like, does this work at scale?
got it.
Rather than what do I personally need on the board for the landing stuff. So
And how do you
that
differentiate? Sorry, the difference between Signal and then Ava are they kind of crossovers at all?
sort of they share a few components. Like it's great when you can share components between boards because then you can just rip from other code bases.
Hmm. Yep.
Um, but Signal is meant to be like machine built and sold, and like you can tell there's no USB port on Signal, so
Got
it's
it.
I program it with a Pogo board,
Hmm.
which is a board that sits on the back. And if you're watching this, you can actually see it right below the R2 on the back. There are four little pads, and there are a few pads elsewhere on the board where you can program it. So that is great if you want to manufacture a product, and if it doesn't need a USB port, why
Hmm.
put a USB port on every one?
Right.
But
Right.
if you're doing development and you're uploading new versions of code every day, and you want to be able to upload code when it's in a rocket, that is a pain in the butt. So
Right. You
um,
don't have to disassemble the rocket, pull it out, put it on the jig, program it,
yeah,
put it back in.
yeah,
Right.
exactly.
Yeah.
Yeah, so Signal is just built to be a commercial product, and Ava is built to fly whatever I want. And I I'd be open to selling it to maybe a few people, but
Right.
mostly it's just for development and test.
Right. Yeah. Keep the best tech for yourself. That's the.
Well, it's not necessarily that. It's mostly just customer
No, no,
service
no.
is
I think that's
awful.
that's that's totally legit. That was said with pride, not with
Yeah,
disdain.
yeah,
So.
yeah, yeah.
Yeah, and I think there is. I mean, there is that element of having to help someone along. If you have people wherever they are in their getting started, of like, hey, I don't even know how to solder yet. It's like, okay, well, this might be
Mhm.
a good starting place for you. It might be good to go a little bit easier, maybe a little bit further. But as someone who has to then support it, then it's like, yeah, that could be kind of problematic.
And speaking of that, so Signal's like a pretty expensive product, relatively speaking. I mean, for what it does, I don't think it's that expensive, but
Hmm.
it's $350 for the entire thrust vector control kit, and
Hmm.
so that's not in a lot of people's price tag.
Yeah.
So the other thing that I did is a series of videos on the channel. If you go to the channel page, it's under the home or playlist actually would work, but it's called Landing Model Rockets, and I think we're at 10, 8 videos, something like
Yeah.
that.
Yeah.
It's not going on anymore, but what I did is I walked people through how you would build and design your own PCB.
Mm.
And so this is the result of it. Um, it's all like if you were just getting started and it was and you didn't, not to say anything bad, but maybe you weren't the best at soldering. This is a great way to get started
That's
because it's all
That's how I
easy to
started. Not great
solder.
at soldering, like I think we all start
Yeah,
there, right?
yeah.
Like that's you need something to have that, to build up your confidence, to also like make you feel like you could design that next thing.
Exactly. So, for some people, they don't want the Signal is like the plug and play solution. Like
Hmm.
you walk through the tutorials, and by the end, you can fly. But a lot of people love the development process, myself included. So, if you wanted to get off the ground with a computer like that, I walked. It's a whole set of tutorials on it. We have a surface mount version too, but I try to have a few different options depending on what you're looking for.
Cool. Yeah, that's great. That's great. So tell me more about the difficulties of rocketry, and how you've overcome them. So you've kind of been building your way up. So I assume, like, as you, and I'm sure you talk about all this stuff as well in the series and elsewhere, but if it's not just going straight up, what are some of the things that you have to think about and control? Is it just those fins like you talked about, or now that you're moving the actual motor as well? Like, where should people start thinking about that modification to make the rocket not just go straight up?
Well, if you're doing this, I mean, I think if you're trying to do a project similar to this, or something that's even just like adjacent, I think the first thing to look at is probably the computer, and to just start writing code and trying to get your feet wet there. I mean, the control theory is the hardest part for me, but I think if you're just getting started, the code is going to be the hardest part.
Got it.
I guess both of those. There's a lot of math that goes into integrating an IMU, integrating like rotation measurements from a gyroscope.
Mm,
Um, and even some of the fancy IMUs that do fusion will not actually work on a vehicle under constant thrust. So like there are problems there. You're gonna have to get used to reading a couple of papers
mm.
to implement that. There aren't a whole lot of examples. I I wish I could say there's like one thing,
Mm.
um, but everything is the one hard thing.
Got it. Yeah. Yeah.
Um,
And
yeah.
so, okay, so then let's just kind of dive down that coding uh, hole. I mean, I think you had mentioned what IMU stands for, inertial measurement unit. But basically, that's just like an accelerometer in your phone or anything else, right? I mean, that's where
Hmm.
these things are sourced from. Um, then what does that spit out to the people that are looking to program and that sort of thing? So is it just coordinates or is it more?
So, an IMU, most IMUs will only spit out accelerometer measurements, which are accelerations measured in meters per second squared, or sometimes they'll do it in Gs, like how many Gs is this accelerating under.
Hmm.
And then it'll also spit out, usually, maybe sometimes a magnetometer, but usually a gyroscope measured in degrees or radians per second. So that is just rotational velocity. It's how fast you're rotating, not necessarily where you're pointing, but how fast you're getting there. And so you can incorporate both of these measurements and do what's called filtering, where you try to use these raw measurements and then get an estimate of, based on these things, based on where gravity is pointed, based on how fast I'm moving back and forth, where am I? And you
Hmm.
sort of integrate these two sensors together to come up with an estimate.
Got it. And so
And
you're ultimately trying to figure out, am I 100 meters off the ground or 1,000 meters off the ground or whatever?
yeah, and that's not even that's honestly, I would think that's the easier part, is integrating to get position or velocity from
Hmm.
the accelerations.
Hmm.
But the more difficult part for a lot of people is the rotation integration. Without getting too much into it, because it's a total rabbit hole,
Hmm.
if you were to rotate, like, you can't just directly integrate the values on the axis, because the IMU follows the vehicle on the board. So if the vehicle rotates 20 degrees on what we'll call the x-axis, and then 20 degrees on what we'll call the y-axis, and then 90 degrees on the roll, when it comes back, how do you represent that it actually has only rolled and not done those pitches and yaws? So it's
Mm,
about
yeah.
it's rotation in three dimensions with, like, I'm going to say a lot of words, but the keywords are, it's strap down inertial navigation,
Hmm.
and all of this stuff is stuff that it's super hard to find if you don't know what to look for.
Right. Yep.
That was the primary challenge for me, is like, no one they don't teach this at music school.
I mean, do
And
they
so,
even
like,
teach
how
this
do
in an
you
aerospace
know?
program
Yeah.
though? Like, is this like literally part of
Oh, yeah.
the curriculum otherwise?
Yeah, if you went to engineering school, you probably, maybe you took a control systems class, maybe you took a mathematics class that dealt with something like this, and maybe it wouldn't be the exact examples, but my biggest challenges were just that I didn't know what to search for. Like, I didn't know the keywords of what I was trying to do.
Hmm. And what about
Yeah,
the need for lots of math? I mean, was that also limiting, or was that something you were able to just kind of work your way into?
I like math. I enjoy doing math, so that's not the problem.
Hmm.
My problem was, a lot of it is done and represented in Greek symbols.
Hmm.
It's going to sound silly, but Greek symbols, like, if you look at a paper and it's just a bunch of Greek symbols, that's like, what is going on here
It's
to
all
me?
Greek to you. You're saying?
It's all Greek to me.
Yeah.
Yeah, I enjoy the math part of it,
Mm,
but sometimes you just have to spend a little bit more time. Like, it's not immediately going to be clear without
yeah.
reading through a paper a couple of times.
I find that when I open like someone's code that I don't it's like maybe pretty complex code, and like I get this like panic feeling, and it's like just like this, oh my god, I don't know anything I'm looking at right now. And then like for me at least, I just have to like try and just like block out just that one little part and just be like, okay, I get this, and then widen the lens and then widen the lens a little more, and like it sometimes works, but yeah, it feels like that's my Greek symbols.
And we do it to ourselves all the time, because if you have, like, still, like, all of the time, I end up, like, ripping someone's code offline from Stack Exchange or GitHub to be like, okay, cool, they've got a driver for this sensor, I'm just going to try it, and I open up the example and it's like, what is happening? And if I had just spent a little bit of time reading the data sheet, it would have been fine.
Yeah, yeah.
Yeah.
That's great. I mean, so okay, so to go back to the IMU thing. So you've just read a data sheet. You've integrated this IMU. You found some code online. It's you're able to talk to it. I assume that the I squared C stuff is already all, or whatever you're using to actually communicate with it, is all figured out by this
Hmm.
point. Uh, and then it's just kind of piping data back. what do you actually do with that data then? So it gets crunched. Does it then, is it ultimately like you're moving a fin or some kind of surface to control that, or?
Yeah, and so this starts to get into what control theory is about. Sort of, it's all control theory. But so let's say you've crunched the numbers and you have your orientation on the vehicle. You know where you're pointed, and you know what your error is. Because if you want to be pointed upright and you're at 2 degrees, you have a 2 degree error. So you take that error, and there's a bunch of ways for you to deal with that. If most people listening will probably be familiar, but if I say the words PID, PID is a type of controller, and a controller is just what we use to try and stabilize some systems. So in your shower example, a PID controller could be used by measuring the temperature of the water, and then it has, it does a little bit of math on that temperature. That's what the PID is doing, and that math is going to spit out a value of how far to turn one of those knobs. So in our case, it would be you give it the error in the orientation, which is 2 degrees, and then the PID math spits out, oh, okay, cool. We need to go -3 degrees in the thrust vector, and that will correct us back to zero.
Yeah.
Um,
And so then
and
you have some element then that will do that correction. Is that the idea?
yeah, it's not. It's mostly, this is where the simulation part comes in too.
Mm-hmm.
What you do with this PID controller is you have a set of what are called gains, and these are pretty much like your control sliders to say how aggressive
Right.
do I want this thing to correct back, or how slow do I want it to be. And so you come up with a set of gains that sort of represent how PID is just a bunch of math. You multiply a thing, then you divide a thing, and you multiply a thing, and that's pretty much it. Um, and when you get those set of gains, that's usually through simulation, where you'll find how sensitive do you want your controller to be, how aggressive do you want it to be.
Mm-hmm.
Um,
Right. To
yeah,
go back to the shower example, how fast you turning the knob, how fast are you stepping out of the way of the
yeah,
of the stream of water?
and you can imagine that can get problematic if your gains are too aggressive, where it gets, the shower is hot, so you turn the cold on way 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 too much, and then the shower is way too cold, and it just goes back and forth like that, because the system doesn't respond instantly. So it's a delicate balance for a lot of this stuff of, where's the sweet spot.
Mm. Yeah. Yeah, that makes sense. And then
Yeah.
so okay, do you know? So then, what actually does the control? What actually changes the physical world that makes it do that correction?
Okay, so it's gone through the PID controller, and like, now how do you make the correction, right?
Mm-hmm.
So it's what I use are just servos, and servos are little motors that you can dial into a specific direction. Here I've got one of the mounts right here. These servos are, here we go. That's this blue thing right here. And so the servo, I send it a command and it rotates. I send it another command and it rotates back.
Mm-hmm.
And I can basically tell it how far I want it to rotate. And by doing that, I can change, if you put the motor right in here, I can change the direction of the thrust.
Mm.
It's really, camera's backwards for me. But anyway, that's what I use, are these little servos to actually make that happen. And with that, once the motor's firing, you close the loop, right? Because that's going to affect your orientation, which affects your error, which
Mm-hmm.
changes the PID output, and the loop is closed.
Right. Right. So as long as you're
Yeah,
not overcorrecting and shooting off the wrong direction or anything like that, you should be able to do that. So
fingers crossed. Yeah.
is it just so to give a audio picture of what's going on here? So that was a rocket motor, like a solid state rocket motor that's actually in like is it just XY, or what is the actual maneuvering of that motor?
So if you're just using one motor, it's just going to be XY, which means you can control the pitch of the vehicle and the yaw of the vehicle. But you could
Mm,
still roll, right? You could still sort of roll around this axis. And because of how the motor is set up, you're not really going to be able to control that roll.
right.
So I have flights where I don't fly any roll control system. And, we don't really roll that much, so it's not a huge problem. As long as you track where the roll is, you can correct for it, or you can, correct for the pitch and yaw. But the other thing that I have, and just suspend your disbelief here for a second at how many wires are in this. So this is a flight computer that's getting ready to go into a rocket.
Mm.
And up at the top of it, I bend some of these wires out of the way. At the top of it is a little wheel that spins
Oh,
with a bunch of screws around the edge.
nice.
And basically, so every action has an equal and opposite reaction.
Wait a
And if
second. Are you
you're
sure about this?
and so if you spin up that mass in the center of the rocket, it's what's called a reaction wheel. You create a torque on the vehicle. And so if you can sense how far the rocket has rolled, and then you can roll in the other direction, or I can't remember, but basically
Right.
then you roll that wheel up, you start spinning it up to correct for that, and you can bring it back to center. And
Oh,
that will
awesome.
work for a finite amount of time because eventually you roll so fast that you saturate the wheel. But for most model rocket flights, it's fine.
Yeah. And how fast does it have to actually react in order to spin up to a significant inertia?
It is pretty. So the motor itself is pretty slow. It's just a 12-volt DC motor. It's like the Jeff Bezos Amazon special, but with a little Adafruit board on it to control it.
Uh-huh.
But
But it's prototyping,
it
right? Sounds like.
yeah, yeah, exactly. I run my control system at 25 hertz, which means that 25 times a second I'm running that math. It's not actually PID, but I'm running some math to say, hey, correct for where we are,
Mm-hmm.
and then sending commands to the servos at the bottom for the thrust vector control mount and the reaction wheel for the roll control system.
Hmm.
The reaction wheel is pretty slow, but it's fast enough to keep us moderately under control.
That's great. That's great. And so you're using like off the shelf components. I love the comparison too because you have these scale rockets, and some of them
Mhm.
fashioned directly after some existing rockets as well, which is awesome. But you're using like off the shelf components. So are there limitations to using non-military, non-rocket, non like NASA grade parts that you have to account
Yeah,
for?
for sure. For sure. Um, yeah, so I don't like at this scale, you don't need a super fancy IMU. You don't need a inertial measurement unit. You don't need crazy high accuracy sensors. And even if you're trying to do this stuff where you're landing and you have to have a really precise control over your timing on ignition for the motor, excuse me, um, like any cell phone grade component is good enough for you to do that. It is incredible what people are able to cram inside little tiny MEMS
Mm-hmm. Yeah.
sensors. Like here, let's see if I can zoom in on the camera and show you. So if I go all the way in, like this right here, if I get really close, you can see the burn marks.
Yeah.
That
Nice.
little square right in the center, that's the IMU, and that
Below the
is
large black
like
square, you're saying, right?
exactly,
Yeah.
yeah, that tiny little square right there is the IMU, and that is good enough. Oh boy, now I have to refocus. That's good enough to fly the whole flight. That's actually the backup, but it's crazy small.
Yeah.
That thing weighs, I don't know, a tenth of a gram, and it gives me all the data I need.
Mm, yeah.
So there's disadvantages to not using something that's military grade, but also like, how am I going to get my hands on that?
Well, in Back to the Future, I think you meet some shady characters in a mall parking lot, and I think that's thanks.
That is the
That's
typical
that's
way,
how it
yes.
goes. Yeah, yeah. You need to trade something for it. Yeah,
Right,
um,
right.
yeah. What I was really wondering though is like because you've been talking about like common filtering and these control systems and things like that, and I had a buddy who did a project on this, and I remember him like he's like, I'm going to use an IMU. I'm going to tell where my boat is, and he's like, so basically he had like the gentle waves, like telling where it
Hmm.
is. But basically the problem was the the amount of error that was accumulating in the system because of just he was sensing every little bob, but then he thought the boat was 4 miles away
Yep.
because of that, and maybe it's well, I'm not sure. Like, is there that kind of error that interacts with your system, or is it kind of like so fast everything's over and done really quickly?
Okay, so I could probably get away. Most of my flights are not more, even on the landing stuff. I don't think we're going to exceed like 10 seconds in the air maximum.
Okay.
And for that, the drift from an accelerometer is going to be pretty much negligible. We had a flight, I think it was like Sprint Flight 8 or 9, where we lost some of the data logging capability on the way up. And we used the telemetry to integrate the accelerometer. And over the course of this 8 to 10 second flight to apogee, um, I think our total error in the accelerometer was maybe, yeah, I think it was this flight. I think our total error was something like a meter or two.
Okay.
It was really, really good.
Yeah.
But I do correct for the drift in any way that I can. So there's a barometer on board which measures the barometric pressure in the air.
Hmm.
And as you go higher in the air, the pressure gets lower. So you can sort of measure that change. And even though the barometer is not very high accuracy, you can use that to sort of correct the drift. You can also use, I have a GPS on board or a GNSS radio, and you can use the altitude estimates from that. Again, not great on their own, but if you filter them all together, they work as a team to, get an estimate of how high are you. Same thing for position and velocity. Like you said, you don't want to think that your rocket's 4 miles away.
Yeah.
So you use those velocity and position updates from the GPS to sort of fill in the gaps. Well, those updates from the GPS are pretty slow. Like you're getting 5, maybe 10 hertz of data, 10 times a second, which is relatively slow in a control system. So that data is noisy, it's slow, and you fill in those gaps between the GPS readings with the accelerometers,
Mm,
integrating those.
right.
So there's a lot of filtering on board. I do use a Kalman filter on the navigation computer, um, and that's another big sort of sticking point that took a long time to tune. I spent a lot of time out in my driveway
Hmm.
sliding a little cart with the computer on it back and forth.
Yeah.
Um,
I mean, yeah, that's
and
like the project that I mentioned. That was his like master's thesis. It was not like a small thing. So it was like, yeah.
No, it's
So yeah,
not.
you're doing many theses of work to get these things working. And
Yeah, and
to compare it to a master's degree, it's actually useful for you. Uh, the output's actually going to do something in the real world. Sorry, just a
Oh,
subtle
jeez.
dig, subtle digs. I didn't. Many people do interesting
I didn't
things.
say it.
Yeah,
I
I
didn't
have
say
no
it.
master's
But
degree. I'm
yeah.
I'm just a schlub over here. So uh, that'll land with like one or two people to be like, yeah, I didn't. Nothing came of what I did.
Yeah.
No, that's
Uh,
great though. And so you're saying that you were able to tune this thing even though it was because you had all these different inputs though it makes it more difficult.
well, yeah. So for you can accept the drift in your sensors, or to correct the drift, you can spend like a month and a half out in your driveway
Hmm.
sliding a cart back and forth, making your neighbors think, "What is wrong with this dude?" Um, so yeah, and it took a while to get right. It's just one of the several things that is like you're going to have to spend a couple of days in a textbook, and you're going to have to watch a bunch of tutorials, and then you're going to be like, okay, I get it. And then another 4 days of compiling errors later, and you have
Yeah,
something that kind of works.
right. So you'd mentioned as well the landings and so this is a separate problem from the takeoffs it seems like. And you're trying to do
Oh
like an
yeah.
actual so now this is like a vertical landing akin to the Tesla rocket on the not the Tesla rocket, Jesus. The
Yeah, you
SpaceX
got it, the
rocket.
Falcon
Yeah,
9.
the
Yeah,
Falcon 9,
yeah.
right? Yes. Um,
So yeah, and I'm adding extra difficulty here. To be fair, I mean, like, it's a model rocket. Like the stakes are very low. If the worst thing that happens is it slams into the
right. The
ground,
parachutes
and then I
usually
can
almost
just,
always work, you're saying?
yeah, usually, almost
Yeah.
always, sometimes.
Right.
So yeah, so anyone who's familiar with rocketry will see like the inherent problem here. When the Falcon 9 comes down, when SpaceX's which one is it? This one. When SpaceX's rocket comes down, they're throttling the motor. They're changing the thrust on that engine so that they can dial in exactly when they get right above the ship or the landing pad, and then they can touch down. And if you have a solid motor like I'm using, just little black powder Estes rocket motors, you can't really throttle those. You can't control the thrust out of them, and inherently, you're going to have some inaccuracies on like between the time that you fired the igniter and the time that the motor actually starts burning. you're going to have inaccuracies in your like variance in how much thrust happens during the burn. And with all of this stuff, it just makes it very difficult to dial in where like when the vehicle is going to land. So if you want to bring up a clip on the channel, Echo landing test 4.
Yep.
Ooh, I think it's 4.
Okay. I
Let's
think
see
I
if
have your
that's wrong.
playlist of many different tries, so that's fun.
Yeah, I think this is it.
So you're dropping it.
This
You're
is
dropping it from a just for an audio picture again. So you're dropping it from a quadcopter, it seems like, and then it's kind of acting once it's being dropped. Is that right?
Yeah, to clarify, so these tests are done now, but I ran a series of tests where I would bring it up with the UAV, separate the vehicles, let the rocket drop, and then the rocket would do its best to try and land upright on the ground. And if you're watching, you can see it gets real close.
Yeah,
It
yeah.
gets right above the ground, and then it just tips
And
over.
then it
Um,
ruins someone's lawn. Just absolutely.
and so you can see how this can work,
Hmm.
but you can also see if you go to go to the next one, landing test 5.
Sure, sure.
Um, the next one has no roll control. We light, I think, late on this. We'll have to see.
I just slowed these
Okay,
down a little bit
so
as well, just for the to
it's
get
fine.
better.
Yeah, so we drop, we light the motor, and it's just wild. We bump into the ground and
Mm,
fall over.
got it. Yeah.
And so you can see like the timing on that is almost identical in terms of what I command the motor to ignite at. So the variance there is just problematic. This is stuff you can learn from simulation too.
Right.
But
Right.
what I'm doing differently for this next set of tests is I'm adding what I'll do in quotations as throttle control. And the way I'm doing it,
Uh huh.
we won't get too into it right now because I'm still deep in the simulation phase to prove it'll work. But so far, it looks like it will. When you're coming down, you don't actually have to change the thrust of the motor. You just have to change where the thrust is pointed. So if you are on the way down and you have a little too much thrust, like you're going to actually land a little above the ground, what you do is you measure where you are versus where you're supposed to be on like the planned trajectory. That'll give you an estimate of your error,
Mm.
and you use that error to do a divert maneuver where the rocket pitches over really hard and starts bleeding off thrust to the side. Then you pitch over back to bleed off the velocity, and
Oh,
then you should be
kind
able
of
to dial
like a
in.
slaloming skier kind of thing. Like you're trying to like hit on
Yeah,
either side and go back and forth, huh?
yeah, exactly. And if you want, I have a video of it on Twitter somewhere, but it might be a little far back,
That's okay. I'll see if
like a
I'll see
few
if I can
weeks.
dig through it, but that's great.
Okay, cool.
I think this
Yeah,
is a
it's
really good view too, though, too, because this is I think it's even easier to see this on the way down than the way up too, of like because you see the top of the rocket kind of going left and right, and then you see the actual engine and the flame that's
mhm.
coming out of it adjusting because of that. That's like a great example of like how a control system needs to work. It's just not quite dialed in enough yet. Um,
Yeah.
how how much like sideways action do you have there? Like because it seems like it's limited in some amount, right? You wouldn't want to shoot it straight out to the side, but maybe you could at some point.
Actually, I would love to shoot it straight out to the side. If I could theoretically go back and forth really, really, really
Hmm.
fast, if you did that enough, then you wouldn't have to pitch over and you could just bleed off your velocity that way. But
What about like
um,
two streams of fire on either side?
people have suggested that
Yeah.
too. That's a much well, in some ways it is a simpler idea, and in some ways
Mm,
it's more complicated.
yeah.
And I don't think it looks as cool as just having one
I mean,
motor,
yeah, right.
but
I mean, that's the thing.
yeah,
Like every sci-fi thing, like there's always rockets landing in sci-fi, right? And they do it somehow.
yeah.
And yeah, when you see it actually happen, it's like, oh wow, okay, okay. Like there's some serious science happening there.
Yeah. So to answer the initial question, we have in the videos that you've shown so far, we have 5 degrees plus or minus. So excuse me, we pretty much have a 10-degree circle that we can roll or pitch and yaw the motor around in, and that allows for a decent amount of control. But there are for the it's hard to explain. There's a lot that's still like in development, but
Sure.
with this new mount that I've been working on, okay, everything's tipping over here. in one direction, where we're not doing the divert, we only have about 4 to 5 degrees of gimbal range.
Mm,
But in a separate direction, we actually have +or -8.
mm.
Um, and that allows for some extremely aggressive maneuvers, in order to get that throttle control working. And so far, simulations say it will work, but there's work to be done.
Yeah, oh, that's awesome. That's, I mean, it it is kind of crazy though that like you have all this stuff going at once. You know, like like you mentioned, there's a lot of yeah moving parts. Sorry, but you know, like you're trying a lot of different vectors to get to the end stage, which is just landing this thing. You know, land or launching this thing and
hmm
then landing this thing. So what else is in the works right now? I mean, what else are you actively investigating?
Well, so the landing is certainly like the flagship project, but I made a conscious effort about a year and a half ago to bring some other projects online because I got worried that, like, I love doing the YouTube thing, and I got worried that, not to assume too much, but I figure I'm probably going to land it at some point. Like, it'll happen through luck or
Yeah,
through
right.
whatever. So I got worried that once that happened, people would be like, "Okay, cool, he did it," and then they would just check out. And
Uh,
so I've started a bunch of other projects to sort of, be like, actually, there's a lot that we can do that's not just landing. Landing's obviously like the cool thing right now in rocketry, but there's a bunch of neat stuff. So I've got a project where I am trying, and it is so much harder than I thought, but I am trying to do a model of Richard Branson's Virgin Orbit rocket.
mm,
And so what they do is they have a 747, and the rocket sits right under where one of the engines would normally sit on the rocket, I think, or on the plane. Either way, the rocket is under the wing of the plane. You drop the rocket sideways, and then the rocket lights midair and then does this big pitch up maneuver and goes to space. And
right.
it's so, they haven't gotten it to work yet, and I haven't gotten mine yet to work yet, but I would like to try that at the model scale.
Yeah.
Um,
The
I
hard
also
the
did a
hard
few
part
other projects.
is, you know, finding all those 747 contractors to really shrink things down, you know.
Oh, it's
Labor
real tough.
disputes and, you know,
Boeing is super busy these
Yeah,
days too. It's just hard
Boeing's
to get in
got some
touch.
stuff going on.
I mean, no disrespect, but yeah. So that's one of the projects. I did a reaction control system, like a gas thruster system, about a year ago, and that project sort of is dead now. But it was sort of a ground demo to show that, like, if you put a bunch of valves in a rocket with a little paintball tank and you pressurized it all to like 3,000 psi, you can spew air out the top just like you would do on a Falcon 9 to reorient it, or a spacecraft would do to
Mm,
change its orientation. And it did work. It worked on the ground.
mm,
It just also started working at the time that I decided to revamp my code base, so
right,
I shut it down.
right.
Yeah.
How do you keep track of everything? I mean, like, it seems like there are a lot of things going on. Not to mention I mean, you got to edit these. I should say you do very beautifully edited videos too. So like
Thank
that
you.
is not a small amount of time either. So, uh, do you have like a schedule or
Yeah, I it used to be. It's getting better.
Uh,
I'm getting better at it. And so far, the thing that has been the most helpful is on most Mondays, except actually, I did not do it today.
oh
We're
no,
recording on
I'm
Monday, but
ruining it.
no, on most Monday mornings, I'll sit down, and I'll shut off my phone, and I'll get a piece of paper, and I'll just write down everything that is like stressing me out that I have to get done.
Mm,
And then I'll try to take that stress away by taking it all and spacing it out in the calendar.
mm.
And that requires you to be really good at estimating how long things will take. And especially, anyone who has ever troubleshooted electronics knows you cannot estimate that. That is, you'd be like, oh, well, I can't get the LED to blink. And maximum, it could take me an hour, right?
Right.
And then an hour later, like, you've desoldered everything on your board. You're like, you've ripped half of your hair out and it still doesn't work.
I
Um,
have a board like literally upstairs, one level, and like it's right before we started recording. I
yep.
took off at least six. I took off every component of the switching regulator, and it's still doing the thing that it's not supposed to be doing. So
I had a problem with Ava uses a switching regulator for the 5-volt bus,
hmm
and so I had a problem about month ago where, and it was right before I wanted to make the Ava video too. So I was hoping I could solve it before the video came out, and I did. The switching regulator was not regulating any of the voltage at all,
mm,
and
we might have the same
it,
part.
it took it took a scope and an oscilloscope and a like a logic analyzer and a bunch of different things to figure out that I had put the wrong resistor on the voltage divider for the switching
The
regulator,
feedback.
and
Yeah.
that was it.
Yep. That'll do it. That's part of what I ripped off today to see if it was it. It was not it for me, unfortunately. That would have been
Oh, I'm sorry.
that would have been great. Yeah. Yeah. It's always good to know that
Yeah.
what that feedback voltage is supposed to be. And that's my old mentor showed me that. He was like, it's like as long as you know it's supposed to be 1.25, you just go right there. And if it's 1 volt,
Hmm.
something's wrong. Like other
Yep.
than
Yep.
yeah, it's great. Boy.
Yeah,
Um,
there's plenty of problems like that too. It's obviously it's real easy to at the risk of tooting my own horn. It's real easy to go to my channel and be like, "Wow, this dude has figured a bunch of stuff out." But there's a ton of stuff that still doesn't work, or
mhm.
there's a ton of stuff that like behind the scenes is still not shown. So like Ava revision 1, like I mentioned, let's just go zoom in here. uh, that burn mark,
Mhm.
I shorted one of the channels on like a high power
Oh
MOSFET,
yeah, yeah.
and it lit right on fire, and it just burned the crap out of the fiberglass. And then there's a linear regulator on the back that would heat up the board to like 140 degrees Fahrenheit.
Mhm. Mhm.
That wasn't great.
Yeah. I mean, you had a video on here. It was how we talk about failures. I think that's
Oh
a
yeah.
great example of that sort of thing. But it's like that is the tough part. You're living your troubleshooting out in the open. You're showing your mistakes. You have
Hmm.
a comment section. You have you have people that are sponsoring you. Like it's tough, right? To do that in the open. How do you deal with that sort of thing?
I'm getting better at it.
Yeah.
Yeah, I'm getting better at it.
Do you teach classes how to get better at it? Because I could use that.
I think honestly, I really think experience is one of the best teachers. This launch is hilarious, by the way. The rocket just falls over.
Oh, then
Boom! There it
and
goes.
then it like goes up
But
the hill. Uh,
yeah, I mean, and this one was live streamed too. It failed on a live stream. That's the other thing. If you want something to work, don't live stream it.
that
Um,
is correct. Yes.
uh, the thing that I've been doing in the last few months is getting just really aggressive about testing on the ground. The worst thing is when you leave the test site, you leave a launch, and you're like, dang, I probably could have figured that out if I had tested a little bit more on the ground.
Mm,
Like, I probably could have found that humidity failure before we went to fly the rocket. I probably could have done XYZ or checked my connections or whatever. Um, and so I've just been like testing the crap out of everything I do. That's helped a little bit.
mhm,
Um, it also is helpful to identify what is an individual failure and what is a systematic failure. So when something fails the same way twice in a row, that is indicative of something a lot bigger and like more problematic, right? So if I have two rockets that fail to deploy the parachutes in a row, I have to like stop flying for a while and reassess like how am I doing testing? How am I doing whatever? Because obviously I've let two of the same things slip through the cracks, and that's
mhm,
that's a lot more serious.
mhm.
Yeah, I don't know. I wish I had better advice. It just you sort of get thicker skin.
Yeah, I think that's great though. I mean, I think that putting yourself out there and just showing your work, it's like personally, as someone who views your work, I mean, like I think it's great to be able to see what you're doing, and I think that there's a there's a vulnerability there because obviously you're saying like, hey, this didn't work, but there's also interest in it, and
Hmm.
and I don't think a lot of people show their work these days. Like it is a lot of just, hey, look at this thing I did. It maybe it took me 3,000 hours, but I'm just showing you the last 5 minutes. Like it's like okay,
Yeah, yeah.
so there is that, but I think it's maybe not everybody wants to see it, but who cares, right? You just go with the people that are interested in seeing the process.
Showing your work is so important too. I know so many of my friends got jobs because they showed their work, like documenting stuff on video. I guarantee if and when BPS stops working and I have to, go apply for a job somewhere else, that whole channel
It's your resume.
is going to be an incredible leg up on anyone else who hasn't documented their work online.
That's right.
I think it's such a, you don't have to give away all the secrets. I don't give away my flight code, although that's more for export control security
Right.
stuff. But yeah, like you don't have to document everything. Just like show that you're making progress on things.
Yep.
I think that's a really
Totally.
valuable thing to do.
Yeah. Whenever I've hired people in the past, it's always been, how do you react to, things going wrong, more than
Mhm.
that they never. If you assume nothing's going to go wrong, you're deluding yourself, right? So it's more important to have that
Yeah.
incremental mindset, I think. So
Mhm, mhm.
that's great. Joe, where can
Yeah.
people find you and follow you and support you?
Well, I tweet too much, so I'm on Twitter at Joe Barnard. I post lots of I post some YouTube videos. There's no like hard upload schedule, but I post YouTube videos on the YouTube channel BPS.space. Um, I have a website, BPS.space. That's the whole thing. That's all you got to type in. There's a bunch of social media pages for BPS too. If you don't want to see me tweet about watching The Good Place or something, I don't know.
I mean, if people don't want to see that, I guess if they're spoilers, but
I don't know what to tell you.
Yeah,
But
right.
yeah, so I don't know. That's pretty much the primary places. And then the way that all of this stuff works, the way that this kid is able to spend so much time like prototyping for toy rockets, pretty much, is through Patreon. So most of the like funding for this project is through just a lot of generous people who are like, yeah, I'll toss you a couple bucks a month. So that's the biggest way to support. But I appreciate anyone just showing up and being a viewer.
Yeah, watching things explode in the right direction.
Hopefully,
Yeah.
hopefully.
Well, Joe, thanks so much
Yeah.
for being on the show, and I'm looking forward to seeing your future failures and your successes.
Thanks so much for having me, Chris. I appreciate it.
So that was our interview with Joe Barnard, and I really enjoyed hearing about his journey towards making rockets that act like real things. And as you saw in some of the clips, if you were watching the video, or if you're listening and you want to go and see some of all of the clips that he does, there is just so much to learn in this field, and it's such a great application of electronics to a real-world goal, as all of our past guests have been. It's all about, what we're trying to show here is people that are using electronics to achieve a goal, and I think that we've had some great guests showing that off so far. If you're not already, you can go and support BPS.space on Patreon. I do that. I recommend other people do that as well. And I encourage you to follow along with Joe. Even if you're not a patron, go and follow along and follow the channel to see what he's building next. Because some of the lessons that he's learning can be applied to your electronics project. And you can use that to build out, maybe not a rocket, but maybe a rover or a piece of electronics that controls something in your house. There's a ton of lessons that you can try and apply from Joe showing them in his everyday dealings with rockets, and you can go and show it for something like controlling your fridge, and your fridge won't blow up. So please follow Joe if you can. Please support this podcast as well if you have the time. We'd love iTunes reviews, or you can share it with your friends on social media. You can find us in social media and all the links below. That's all for now. We'll see you in the next podcast, and thanks for watching.